Hello, everyone. In this video, we are going to look at the strategy for integrating a rational function. And this is on the second page of our notes for section 5.5. So in the previous video, we looked at an example of computing an integral using partial fraction decomposition. So it turned out this integrand that we used has a specific form that signaled to us to set up partial fractions in this way. So depending on what this integrand looks like will affect what fractions we set up. So let's look at the scenarios of what the integrand looks like in order to determine what those fractions are going to be. So focusing on rational function. So a rational function is a function that's composed of a fraction like this. We call it a rational function. So now we are going to look at three different scenarios for what the denominator function looks like. So in these three scenarios, again, we're just looking at the denominator function, which we're calling q of x. And whenever we're doing this strategy, we're always only going to use integrands or rational functions where the denominator function has a greater degree than the numerator. And the reason this is so is because if the numerator had a larger degree, then we could divide q of x into the numerator. And so we're called degree. Is this the highest exponent on the variable? Okay, and in the examples that we look at and the problems that we do in this class, we're always going to be looking at integrals that have this, that are satisfying this, where the denominator has a larger degree than the numerator. Okay, so let's look at these three situations for what the denominator function could look like. Okay, so if that denominator function, q of x, contains a linear factor, which means it has a factor that looks like x minus some constant. So notice x minus c, that is an equation of a line. So that's what we call equations of this form, linear factors. Notice the power on x is just 1. So if we're in this case, then we use a partial fraction of the following form. So then we just use one fraction that looks like a over x minus c. So recall in the first example 1 in the previous video, q of x contained 2 of these linear factors. So that means we used 2 partial fractions of this form because we had a linear factor x minus c. We also had one that said was x plus d. So that means that was why we had to use another factor of the form b over x plus d. So for each linear factor in the denominator, we need to use a partial fraction of this form given in this first scenario. Okay, so just to summarize, example 1 fell into this type of situation. Okay, but the denominator could also look like our second scenario, where that denominator contains a repeated linear factor. So in example 1, we had 2 different linear factors, so it wasn't repeated. So this means our linear factor, x to the power of 1 minus c, was also raised to an exponent. In this case, we need to use multiple partial fractions, and they need to look like this form. So we're going to have x minus c in the denominator. Our first fraction is going to be raised, the denominator will be raised to the 1, and then we have a constant a sub 1 in the numerator. Then we have another fraction where we have that x minus c in the denominator, now raised to the 2, with a different constant a sub 2 in the numerator. And now we're going to have enough fractions so that we include all the way up to our largest repeat of that linear factor. So our final partial fraction will include x minus c to that n power in the denominator. And our constant we can call a sub n. Okay, and now the final type of rational function we're going to look at is when that denominator contains a factor that has a 2 on the exponent of the x. So meaning a polynomial factor. And that it's irreducible, meaning we can't write it as smaller linear factors. Because if we can, then that means we're in a previous scenario. Okay, so in this situation, when we have an irreducible degree 2 factor, then we use partial fractions analogous to 1 and 2. So meaning if this factor is raised to 1 power, then we use 1 fraction. If it's raised to a power of n, then we need to use n fractions. But now the numerator changes slightly. Rather than just including a constant numerator, our numerator will have the form ax plus b. So that means the fraction will look like ax plus b over x squared plus cx plus d. And this will repeat if we have a repeated second degree polynomial. Okay, so this was kind of a lot to take in, but it's really important that we revisit this strategy for decomposing a rational function. Now, this will start to make more sense when we look at example 2, when we're going to look at many different rational functions and decompose them into their partial fractions. So take a look now at example 2. Come back to this video for more clarity as we work through examples of these various scenarios.